Hello, friend. So glad you're here tonight. Get comfortable, pull the covers up, and let the day loosen its grip. There's nowhere else you need to be. Before we begin, a small request. Most of the people listening tonight aren't subscribed. If this channel has ever helped you drift off, take a moment to subscribe and tap the like button on tonight's video. Both are free, they take 2 seconds, and they help this channel more than you'd think. And you can always change your mind later. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is where you are. I love reading them. Tonight is a slow drift through the real story of the moon, one true thing at a time. There is nothing to do here and nothing to remember. Each one will pass like a slow cloud, some familiar, some quietly surprising, all of them real. If you fall asleep somewhere in the middle, that is exactly how this is meant to work. Settle in, let your breathing slow down, and we will begin. One more thing before we begin. I'm also a co-founder of a sleep app, built to be the most affordable one out there. No ads, ever. Just sounds and stories made to help you sleep. It may not be released yet as this video goes up, but if you're watching a little later, it might be out by now. Just search for it. It should be easy to find. It works on iPhone, Android, and everything in between. Downloading it is the best way to support this channel. The Lion Nebula roared to life with NASA's Webb article 6 days ago. This nebula, a cloud of gas and dust, is now visibly changing, becoming more active. The process involves the birth of new stars within the nebula, which emit light that we can observe from Earth. NASA's James Webb Space Telescope has provided high-resolution images that reveal these changes. The telescope's advanced technology allows us to see details never before visible, showing the nebula in a new light. This recent activity is a natural part of the nebula's life cycle, where it goes through phases of quiescence and renewed star formation. The Lion Nebula's distance from Earth makes it challenging to study, but with Webb's capabilities, we can now observe these events in unprecedented detail. The process of star formation within the nebula releases vast amounts of energy, causing the gas and dust to glow brightly. This renewed activity indicates that the nebula is entering a phase of increased stellar productivity. The high-resolution images from Webb reveal intricate structures and movements within the nebula, providing valuable insights into its evolutionary stages. Observing these events in detail helps scientists understand the complex dynamics of star formation in interstellar clouds. The nebula's transformation offers a glimpse into how stars are born and evolve, shedding light on fundamental processes in our universe. This understanding is facilitated by the telescope's infrared capabilities, which penetrate the dense gas and dust to reveal underlying structures. The detailed observations allow scientists to study the physical conditions necessary for star formation, providing crucial data for theoretical models. As more data is gathered, it becomes clear that these changes are part of a continuous cycle, with new stars being born even as older ones fade away. The Artemis program is named after the Greek goddess of the hunt, wilderness, and the moon, Artemis. This name reflects our deep connection to nature's beauty. The moon has long held a place in both mythology and science. NASA's Artemis program aims to explore it further, seeking new insights into its mysteries. The lunar surface, illuminated by sunlight, holds clues to the past. Its craters, formed over billions of years, are silent witnesses to ancient impacts. The distance between Earth and Moon is vast yet measurable, with light taking just over a second to travel between them. Our understanding of this celestial body grows with each exploration, revealing more about its role in our solar system. Each expedition uncovers more about the lunar soil and its composition, helping scientists understand the moon's formation. The reflective nature of the moon's surface allows telescopes on Earth to observe it in detail, providing valuable data. Careful study of lunar rocks brought back by missions has revealed the timeline of events that shaped our solar system. Exploring the moon's polar regions could reveal frozen water, hinting at potential resources for future missions. The moon's surface, pockmarked with craters, bears evidence of countless cosmic events. Its bright glow against the night sky inspires curiosity and scientific inquiry. Lunar samples, carefully studied under microscopes, reveal a complex history spanning billions of years. The more we observe and explore, the deeper our knowledge of this celestial neighbour grows. The dark side of the moon, forever turned away from Earth, remains a puzzle waiting to be solved. Each grain of lunar dust tells a story of its journey through space. The constant bombardment by micrometeoroids slowly alters the moon's surface over time. Observing these changes helps us understand the ongoing evolution of our celestial neighbour. The Artemis program involves innovative technologies to explore more of the lunar surface. This initiative, named after the Greek goddess of the moon, reflects humanity's enduring fascination with our celestial neighbour. NASA is building an Artemis base camp on the moon's surface as part of its plans for sustained exploration. The Roman counterpart to Artemis is Diana, signifying the goddess's influence across different cultures. These explorations aim to uncover more about the lunar surface and its secrets. The innovative technologies used in the Artemis program are designed to traverse and study the lunar terrain in greater detail than ever before. The moon's surface, marked by craters and dust, holds numerous mysteries waiting to be revealed. As NASA continues to develop and deploy these technologies, our understanding of the moon deepens. The Artemis program's advanced robotic systems will map the moon's composition, revealing its geological history. These missions seek to understand how the lunar surface evolved over billions of years. By studying lunar samples and images, scientists gain insights into the moon's past environment and potential for future resources. The moon's surface is a palimpsest, where each crater and layer of dust holds clues to past impacts. These traces can be deciphered by analysing the composition and distribution of lunar regolith. Advanced spectrometers aboard Artemis missions will help scientists interpret these clues. Comparing lunar data with meteorite samples from Earth allows for more precise dating of lunar events. The moon's surface, scarred by countless impacts, preserves a record of ancient celestial collisions. Each crater is a snapshot of a past event, etched into the lunar landscape. By examining these formations, scientists can piece together the timeline of cosmic occurrences. Comparative analysis with Earth's geological history offers insights into the shared origins of our solar system. The Apollo missions left behind scientific instruments and American flags on the lunar surface. Humans have spent only about 12 days on the moon in total, all from those Apollo missions. These brief visits provided valuable samples of lunar rocks. The rocks helped scientists understand the composition and formation history of the moon. The flag and instruments are still there, untouched by human hands for decades. They stand as silent witnesses to humanity's exploration. Each item left behind tells a story about our desire to know more about the cosmos. Despite their short stays, the Apollo astronauts brought back pieces of the moon that continue to reveal its secrets. The moon's untouched state preserves the traces of our early forays into space, offering a pristine record of human exploration. These remnants on the lunar surface remain undisturbed by further visits, maintaining their historical integrity. They serve as tangible evidence of humanity's initial ventures beyond Earth's atmosphere. Each item left behind has weathered the harsh lunar environment, bearing witness to the passage of time. The flags and instruments, exposed to constant sunlight and darkness cycles, exhibit signs of degradation over time. Each object's condition reflects its unique exposure to space radiation and temperature extremes. The lunar regolith beneath the flags has shifted slightly due to meteoroid impacts, subtly altering the landscape. These artifacts, once pristine, now bear the markings of their long isolation in the harsh lunar environment. These remnants, frozen in time, hold secrets about the lunar environment and its effects on materials. The flags and instruments have endured the moon's extreme temperatures, from scorching sunlight to frigid darkness. Observations from spacecraft have allowed scientists to monitor changes over time. Subtle shifts in the artifact's positions offer clues about lunar dynamics. A fact about the moon is that 100 million years after its formation, heat was still present in its interior. This indicates that the moon's thermal state remained significant even over such a vast period of time. The heat within the moon suggests that its core may have cooled at a slower rate than expected. possibly due to the presence of radioactive elements. These elements can generate heat as they decay over billions of years. Scientists came to this understanding by studying the way light reflects off the lunar surface and how it has changed over time. The moon's craters and regolith also provide clues about its thermal history, showing that the interior was still active long after its formation. The lingering heat within the moon also suggests that its interior is not as rigid as once thought, allowing for some degree of flexibility. This flexibility can be attributed to the gradual release of energy from the decaying radioactive elements deep inside the moon. The evidence for this ongoing process comes from the subtle shifts in the moon's surface, indicating a slow but steady reshaping over time. Additionally, the reflection and absorption patterns of heat across the lunar surface provide further insights into the moon's thermal dynamics. The presence of heat deep within the moon implies that its interior is not entirely solid, but likely contains pockets of molten material. The slow release of heat from these areas contributes to the subtle shifts observed on the lunar surface. The gradual cooling process indicates a complex thermal evolution that has shaped the moon's internal structure over billions of years. Scientists have used thermal imaging techniques to map the distribution of heat across the lunar surface, further supporting the notion of ongoing internal activity. The core mantle boundary of the moon, where the inner core transitions to the outer mantle, is estimated to be about 350 kilometers beneath its surface. This boundary marks a significant change in the physical properties of the lunar interior, with different densities and compositions of materials on either side. The exact depth of this boundary has been determined through seismic data gathered by instruments placed on the moon's surface during various space missions. These measurements help scientists understand the structure and formation history of our natural satellite. This layer is crucial in shaping the moon's gravitational field, which affects its orbit around Earth. Over time, studies of these layers have led to a deeper comprehension of how celestial bodies form and evolve. The boundary's depth reveals that the moon has a partially differentiated interior, similar to Earth. Seismic waves travel at varying speeds through this layer, allowing scientists to deduce its composition and structure. The slight wobble in the moon's orbit, known as lunar libration, is influenced by this boundary, providing further insights into its internal dynamics. By studying this transition zone, researchers can better understand the early stages of planetary formation. This transition zone provides clues about the moon's early magma ocean phase. The density change across this boundary suggests a gradual cooling and solidification process. Seismic reflections reveal varying material densities, indicating compositional changes. These findings help reconstruct the lunar interior's evolution over billions of years. This boundary, separating the core from the mantle, is thought to be caused by a shift in material properties. Its precise location was mapped out using seismic waves' travel times. These variations in speed suggest different materials and structures within the moon. This knowledge helps in modelling the moon's internal dynamics over time. The Canadian Lunar Research Network conducts research on the interior structure of the moon using various instruments and methods. This network employs instruments that detect seismic activity, gravity variations, and other signals reflected off the lunar surface. By studying these subtle changes, scientists can map out the hidden layers beneath the crust. The moon's core is believed to be dense and perhaps even partially molten. These observations are made possible through satellite-based instruments that orbit the moon, collecting data continuously. Over time, this data helps build a detailed model of the lunar interior. Understanding the moon's structure can provide insights into its formation and evolution. The research methods involve sophisticated analysis of signals reflected off the lunar surface. This data is vital for comprehending the moon's geological history and its role in our solar system. These reflections can reveal shifts in the moon's gravitational field, hinting at subsurface structures. The density variations beneath the surface influence how seismic waves travel. By comparing these observations with models of lunar composition, scientists infer the nature of the hidden layers. This intricate process is akin to listening for echoes within the moon. Each seismic wave provides a unique signature, offering clues about what it passed through. Subtle differences in travel times and amplitudes reveal varying densities and compositions. These minute variations can indicate the presence of large impact basins or other subsurface anomalies. The collected data is meticulously analyzed to refine our understanding of the lunar interior, layer by layer. These delicate seismic signals allow scientists to construct an internal map of the moon. By carefully studying their paths, researchers can discern different materials and structures. Each wave's journey reveals hidden complexities within the lunar interior. These observations are made possible by advanced instruments that track even the smallest shifts in gravitational fields. The surface temperature of the moon can vary from 107 K, 666 degrees C at night to 3090 K, 1170 degrees C during the day. This vast swing in temperature occurs because the moon lacks an atmosphere to retain heat. As a result, the lunar surface quickly cools when the sun's light is not illuminating it. The intense heat of the daytime is due to the direct sunlight hitting the moon's surface. Scientists have measured these temperatures using instruments placed on the lunar surface during Apollo missions and other robotic explorations. The moon's rotation is synchronized with its orbit around Earth, which means one side always faces the sun while the other is in darkness. This constant cycle of light and dark creates these extreme temperature changes. The absence of an atmosphere on the moon allows these temperature swings to occur unimpeded. This extreme variability is a consequence of the direct exposure of the lunar surface to the sun's heat. Over time, data from various instruments has confirmed and expanded our understanding of this phenomenon. The lack of any significant wind or weather on the moon means that these temperature changes are not smoothed out over time. This direct exposure to solar radiation leads to rapid heating and cooling cycles. By studying how quickly the lunar surface responds to sunlight, scientists can better understand the thermal properties of regolith. This rapid heating and cooling also affects lunar structures, causing them to expand and contract at significant rates. The lack of any moisture or gases on the moon prevents these changes from being mitigated in any way. Observations made during both daytime and nighttime have shown that even small craters exhibit dramatic temperature shifts. This continuous cycle of thermal expansion and contraction influences the stability and lifespan of lunar features. The lunar day is about 29.5 Earth days long, meaning the moon takes nearly a month to complete one rotation on its axis. This slow spin is due to the strong gravitational pull of our planet, which has caused the moon's rotation to synchronize with its orbit around the Earth. As a result, we see mostly the same side of the moon, known as the near side, while the far side remains largely hidden from view. The average distance between the Earth and the moon is approximately 384,400 kilometers, or about 238,855 miles. This vast separation contributes to the moon's slow rotation. Astronomers have observed that a full moon occurs when the moon is directly opposite the sun, with the Earth standing between them. Over time, careful observations and calculations have allowed us to determine the precise length of the lunar day. The moon's slow rotation ensures that sunlight consistently reaches one hemisphere during each lunar day, leading to extreme temperature variations between its day and night sides. This tidal locking is a result of Earth's gravitational influence, which has also shaped the moon's oval orbit. The consistent visibility of the same side of the moon has facilitated detailed mapping by astronomers using telescopes and lunar probes. This synchronization creates a state known as tidal locking, where one side of the moon always faces Earth. Observations from lunar missions have confirmed this alignment, showing the same familiar craters and Maria on the near side. The slow spin allows for continuous illumination on one hemisphere, while the other remains in constant shadow. This consistent orientation has allowed scientists to study the composition and topography of the moon's surface with greater precision. Ancient Greek astronomers like Aristotle and Ptolemy wrote about the moon's phases and motion. They observed how the moon changes its appearance over time, waxing and waning in a cycle that repeats every month. This regular pattern of light and dark on the lunar surface caught their attention, prompting them to document what they saw. By carefully noting these changes, they began to understand the mechanics behind the moon's phases and how it moves across the night sky. They realized that as Earth orbits the sun, it casts a shadow on the moon, creating different phases. This shadow shifts gradually, illuminating more or less of the lunar surface. Their observations were made by gazing at the night sky, tracking the moon's position and appearance over several months. The Greeks noted that when the moon is between Earth and the sun, it appears as a thin crescent. As it moves further from the sun, more of its surface becomes illuminated until it reaches full brightness. The dark portion of the lunar surface remains unseen during this cycle. Over time, the Greeks deduced that the moon does not produce its own light, but rather reflects the sun's rays. The Greeks understood that the moon's phases are a result of the angle between Earth, sun, and moon. They saw that when the moon is full, it lies opposite the sun in the sky. Their detailed observations revealed how the lit portion of the moon changes size and shape nightly. By tracking these shifts over many months, they learned that the cycle repeats every 29.5 days. Galilei observed the moon through a telescope in 1609, leading to more precise maps of its surface. This was the first time such an instrument was used for lunar observation. The moon's surface, until then shrouded in mystery, began to reveal its secrets. Galileo's observations were meticulously recorded, paving the way for future astronomers. His work, published on January 7, 1610, included detailed drawings of the lunar surface. These early maps, though crude by today's standards, marked a significant step in our understanding of the moon. The light from distant stars and planets, once thought to be perfect spheres, now showed imperfections. This discovery changed how we perceive and study celestial bodies. The moon's surface, once a smooth and perfect sphere in the minds of ancient astronomers, was now understood to be irregular and complex. This revelation came about through the systematic observation and documentation of lunar features seen through Galileo's telescope. The detailed drawings made by Galileo served as a blueprint for further exploration and understanding of the moon's geology. As more observations were collected, it became clear that the moon was not a static and unchanging entity, but rather a dynamic body with varied terrains and structures. The moon's topography, visible through telescopes, displayed mountains and craters that challenged previous notions of a uniform surface. Observations over time revealed patterns in these features, suggesting they were not random but shaped by past events. Detailed drawings of lunar phases captured the progression of shadows, indicating the presence of light and dark areas on the moon's surface. Further analysis showed that these areas varied in size and location over the lunar cycle, implying a complex geological history. Uncrewed missions like Lunar Reconnaissance Orbiter, launched on June 18, 2009, continue to study the moon. This orbiter circles the lunar surface, collecting valuable data. It has been instrumental in lunar exploration since its launch. The orbiter has helped discover intriguing features like lava tubes hidden beneath the surface. These tubes could provide shelter for future human missions. The Lunar Reconnaissance Orbiter uses advanced instruments to map and photograph the moon's terrain. Its high-resolution camera captures detailed images of the lunar landscape. The data gathered help scientists understand the moon's geology and history better. This continuous study is crucial for future space exploration plans. The orbiter also detects changes in the lunar surface over time, such as shifts in crater shapes or newly formed impact sites. By mapping the moon's gravity field, it reveals areas of higher density beneath the surface, suggesting buried resources like water ice. This data is crucial for planning safe and efficient landing zones for future missions. Additionally, the orbiter monitors the lunar environment, measuring radiation levels that could pose risks to human health during prolonged stays on the moon. This continuous monitoring enables researchers to detect subtle alterations in lunar geology that might not be visible from Earth. The orbiter's precise measurements allow for detailed modeling of the lunar surface and subsurface structures. By analyzing these data, scientists can predict potential hazards and optimal sites for future landings. These insights are essential for crafting strategies to navigate the lunar environment safely. The Lunar Reconnaissance Orbiter's findings indicate potential habitability under the lunar surface, enhancing our understanding of its geological composition. The presence of lava tubes suggests stable structures that could shield human habitats from radiation and micrometeoroid impacts. This knowledge was obtained through detailed analysis of the orbiter's imagery and gravitational data. Such discoveries provide a roadmap for designing sustainable lunar bases in the future. Daytime temperatures on the Moon can reach as high as 260 degrees Fahrenheit or 107 degrees Celsius. This is due to the intense sunlight that bathes the lunar surface. The equator of the Moon, in particular, experiences these extreme temperatures. Scientists have measured daytime temperatures on the Moon using remote sensors and probes sent by various space missions. These temperatures can rise up to 400 K, which is equivalent to 107 degrees Celsius. Under the direct sun, the lunar surface becomes incredibly hot. The lack of atmosphere on the Moon allows sunlight to directly heat its surface without any interference. This intense heating is a result of the Moon's position in the solar system, where it receives direct sunlight without any atmospheric protection. The absence of an atmosphere also means there is no heat retention overnight, leading to significant temperature swings. These findings are based on observations from lunar landers and orbiting spacecraft, which have provided valuable data on the Moon's thermal conditions. The lack of an atmosphere on the Moon also means that temperatures at night can drop to extremely low levels, sometimes as low as 173 degrees Celsius. This day-night temperature difference is dramatic and highlights the importance of sunlight in heating the lunar surface. Data collected by thermal cameras mounted on spacecraft have revealed these temperature variations across different regions of the Moon. Additionally, the Moon's tilt is minimal, which contributes to the uniform distribution of these extreme temperatures across its equatorial region. The lunar surface bakes under the unfiltered solar rays, unable to dissipate heat through convection or retain it at night. Temperature shifts on the Moon are so stark that they can fracture rocks due to thermal stress. This extreme heating and cooling cycle is a consequence of the Moon's proximity to the Sun and its lack of an insulating atmosphere. Observations from lunar rovers have shown these temperature swings over short distances, illustrating the Moon's harsh thermal environment. The hottest temperature ever recorded on the Moon was about 400 Kelvin, equivalent to 107 degrees Celsius. This occurs when sunlight hits a lunar surface tilted towards the Sun, warming it significantly. Conversely, at night, the lack of atmosphere allows temperatures to plummet. The coldest temperature ever recorded on the Moon was around 30 Kelvin, showing the extreme swings in lunar weather. These temperatures were measured using remote sensors placed on the Moon's surface during various missions. The differences highlight the stark contrast between the sun-facing side and the dark side of the Moon. These extremes in temperature are due to the Moon's lack of atmosphere, which prevents heat from being retained or distributed evenly. Remote sensors placed on the lunar surface during various missions have provided valuable data about these thermal variations. The extreme cold is a result of the absence of any external heat sources other than direct sunlight. These measurements help scientists understand the complexities of the lunar environment and its interaction with solar radiation. When sunlight is absent, the lunar surface quickly loses heat due to its lack of insulating atmosphere. Over time, this loss can be significant, leading to extremely low temperatures during lunar nights. Remote sensors continue to monitor these changes in real time, providing data on how solar radiation affects lunar temperature. The absence of wind or other atmospheric conditions allows the surface to directly radiate heat into space unimpeded. The lack of an atmosphere on the Moon also means that there is no wind to mix warm and cold air, leading to even greater temperature differences across the surface. Remote sensors have detected these variations by measuring infrared radiation emitted from the lunar soil. The data gathered shows a clear pattern where the temperature changes are most severe near the poles due to the unique angles of sunlight exposure there. The temperature of the Moon changes dramatically due to its rotation and the Sun's angle. This is because the Moon does not have an atmosphere to trap heat, so it experiences extreme temperatures when facing or away from the Sun. On the sunlit side, temperatures can reach up to 260 degrees Fahrenheit. while on the dark side, they drop as low as 280 degrees Fahrenheit. This happens because there is no air to distribute the heat evenly across the lunar surface. When sunlight hits the moon, it heats up the surface directly beneath it, creating these vast temperature differences. The lack of an atmosphere also means that the moon cannot retain heat for long periods. As a result, the temperature on the moon's surface can vary significantly depending on its position relative to the sun. These drastic temperature swings occur within a single lunar day, which lasts about 29 Earth days. Astronauts on future missions will need to be prepared for these extreme conditions. The lack of atmosphere also means that the moon has no wind to redistribute heat, further intensifying these temperature variations. The moon's temperature swings also affect lunar exploration, requiring equipment designed to withstand both extremes. This has been observed and measured by thermal sensors on spacecraft orbiting the moon. Scientists use these data to understand how heat affects the moon's geology and potential habitability. These temperature shifts on the moon can cause equipment malfunctions and complicate scientific measurements. Without an atmosphere to regulate heat, materials on the lunar surface expand and contract rapidly, leading to stress fractures and other damage. The extreme temperatures also pose challenges for human health and safety in future habitats. Observations from orbiting satellites have shown that these temperature variations are most pronounced near the poles of the moon. Researchers from Brown University and Lunar Scope have mapped the moon's regolith thickness using data from over 300 small craters. The mapping process involved analysing the depth and composition of these craters to determine how thick the lunar soil, or regolith, is in various regions across the moon. This data helps scientists understand the geological history of the moon and can be used to plan future exploration missions more effectively. By studying small craters, researchers gain insights into the larger landscape. The map created by these efforts provides valuable information for potential landing sites and resource extraction. It is publicly available, ensuring that the knowledge gained from this research can be accessed by others in the scientific community for further study and application. Understanding regolith thickness aids in estimating the stability and composition of landing sites, ensuring mission safety. It also informs resource extraction strategies by indicating where water ice or other valuable materials may be concentrated. The data was gathered using sophisticated instruments that measure crater depth with high precision. This research underscores the importance of small-scale studies for unveiling large-scale lunar features and processes. The depth and composition analysis reveals how long lunar soil has been accumulating, hinting at the age of different regions on the moon. The thinness or thickness of regolith in certain areas can indicate past impacts or volcanic activity that shaped the lunar surface over time. By examining small craters, researchers deduce the erosion rates and evolution patterns of larger formations. This approach offers a window into the dynamic processes that continually reshape the moon's surface. Scientists have studied the thickness of the moon's surface, called regolith, over its near side using radar data from Earth. This method sends signals that bounce off the moon's surface and return to us. The time it takes for these signals to travel gives us information about the distance they covered. By analysing this data, researchers can estimate the depth of the regolith layer. Radar waves penetrate deeper into the lunar soil than visible light, allowing us to explore beneath the surface without leaving Earth. These radar waves are longer than light, which helps them pass through the surface. They reveal what's hidden underneath, offering a glimpse into lunar geology. This method is non-invasive, preserving the moon's pristine state for future exploration. By studying these data, we can understand more about the moon's formation and evolution. This technique uses radio waves that can travel through solid material, giving scientists a unique tool to probe beneath the moon's surface. The lunar regolith's thickness varies across different regions, providing insights into its composition and history. By comparing these depth measurements with geological models, researchers can reconstruct past events that shaped the moon's surface. This non-intrusive method ensures that any future human missions find a well-preserved environment to explore. Radar data has been used since the Apollo era, providing a consistent method for studying the moon. By comparing these signals to those reflected off known surfaces, scientists can calibrate their measurements. The unique properties of lunar regolith, such as its granular nature, absorb and scatter these waves differently than smooth rock or metal. Over time, these radar studies have built up a detailed map of the moon's subsurface, offering insights into its geological processes. The angle of slopes for lunar lava tube formation ranges from 0.4 degrees to 6.5 degrees. These slopes are crucial, enabling molten rock to flow smoothly within the tubes. The lower angles allow the lava to maintain steady motion without rapid cooling or solidification. Over time, these tubes have been revealed through study of lunar terrain. Careful examination of images from spacecraft has uncovered their subtle presence. The gentle angles indicate a gradual process of formation, shaped by the moon's low gravity and quiet environment. No sudden shifts or steep declines interrupt the flow within these tubes. This understanding comes from meticulous analysis of lunar surface features, offering insights into the moon's geological past. These formations provide a unique glimpse into the internal structure of the moon. The low angles suggest a calm and consistent geological process. Further study involves comparing these slopes with volcanic features on Earth. This reveals similarities and differences, enhancing our comprehension of both bodies. The consistent slope angles also imply a steady lava supply, indicating prolonged volcanic activity on the moon. Researchers observe that these slopes are indicative of efficient heat transfer within the tubes, preventing sudden cooling. The lunar regolith's low cohesion allows for smooth lava flow without significant resistance. Overlaying images from different lunar phases helps trace the evolution of these tubes over time. The uniformity of these angles points towards a stable lava supply, enabling the tubes to extend uninterrupted. The moon's low gravity facilitates this steady flow by reducing resistance. High-resolution imagery from orbiting spacecraft allows for precise measurement of these slopes. The lunar terrain's subtle variations over time are captured in sequential images, aiding in the understanding of tube formation. The Mare Tranquillitatis pit is associated with a lunar lava tube, an intriguing geological feature hidden beneath the moon's surface. Scientists believe that this lava tube, located within the tranquil sea of Mare Tranquillitatis, was formed during volcanic activity long ago. The lunar lava tube stretches deep into the moon, a remnant from a time when the moon was more geologically active. Researchers have studied the pit using detailed imagery and data analysis, leading to the discovery of this ancient tunnel. The University of Trento, in collaboration with NASA JPL Caltech, has contributed to creating artistic concepts that depict the lunar lava tube within Mare Tranquillitatis. These visualizations help scientists better understand the structure and extent of the lava tube, providing valuable insights into the moon's past and its internal workings. The lava tube is thought to have formed through the cooling and solidification of lava flow, creating a natural tunnel beneath the moon's surface. Researchers hypothesize that these tubes could provide shelter for future lunar habitation due to their stability and potential to shield from radiation. Advanced imaging techniques and topographic data analysis have been crucial in mapping the precise location and dimensions of this underground structure. As studies continue, scientists aim to uncover more about the geological history of the moon, including the processes that shaped its interior. This lava tube, formed by the slow cooling of molten rock, provides a glimpse into the moon's early volcanic activity. Its discovery was made possible through high-resolution lunar images and digital elevation models. The stability of these ancient tunnels makes them attractive for potential human habitats on the moon. Further exploration is needed to fully understand their extent and structural integrity. The IDW estimation method has been used to derive gridded maps of lunar regolith thickness, mapping the depth of the moon's surface. This method estimates by using measurements from specific points across the moon's surface. 68 distinct points have been carefully selected for their readings, which are then used in the inverse distance weighted estimation to create an accurate map of the lunar regolith thickness. These points are chosen for their precision and distance apart, ensuring a comprehensive representation of the moon's surface. The light from the sun that hits these measured points helps scientists understand the depth and variation of the lunar soil. Over time, These readings have been collected and analysed to provide a detailed map of the Moon's regolith thickness using the IDW method. This approach allows scientists to interpolate data from these selected points, filling in the gaps between them with estimated values. The further away a point is from the measured locations, the less influence it has on the final map's accuracy. By combining multiple datasets and using the IDW method, researchers can enhance their understanding of the Moon's surface. The resulting gridded maps provide insights into the distribution and variation of lunar regolith thickness across different regions of the Moon. The use of solar light in these measurements aids in determining the depth and heterogeneity of lunar soil by analysing shadows cast on the surface. The selection criteria for the measurement points emphasise both spatial distribution and data quality to ensure that every region is well represented. The IDW method, leveraging distance as a key factor, assigns greater weight to closer points in the estimation process. Continuous refinement of these gridded maps allows scientists to better anticipate the lunar surface characteristics for future missions. Regolith thickness maps are shown in Lambert azimuthal equal area projection. This projection ensures that the Moon's regolith, a mixture of soil and rock debris covering its surface, is depicted accurately. It allows for the even distribution of the regolith data across the lunar surface, preserving both the size and shape of features. By using this method, scientists can analyse the thickness of the regolith layer over different regions of the Moon. This analysis helps in understanding the geological history and composition of the lunar surface. The maps are created using data gathered from various lunar missions. They provide valuable insights into the Moon's evolution and the processes that have shaped its landscape over time. The Lambert azimuthal equal area projection ensures every region on the lunar surface is represented proportionally. By evenly distributing regolith data, this method minimises distortion at the poles and equator. This accurate depiction aids in identifying areas with varying regolith thickness, crucial for planning future lunar missions. The analysis of these maps contributes to our understanding of how impacts and volcanic activity have influenced the Moon's surface over billions of years. The regolith's distribution provides clues about where impacts have occurred, shaping craters and ejecta patterns. This uniform projection aids in detecting subtle variations that might indicate areas of greater stability or hazard. The careful mapping also reveals regions affected by ancient lava flows, contributing to the lunar surface's evolution story. By examining these maps, researchers can better predict where to safely land future probes and rovers. The data used for creating the regolith thickness map includes information from lunar missions dating back to the 1970s. Over time, these missions have collected valuable samples and measurements from various points on the Moon's surface. The regolith, which is essentially a layer of dust and small fragments covering the lunar surface, varies in thickness across different regions. This variation can be attributed to numerous factors, such as the frequency of meteor impacts and the composition of the underlying bedrock. By analysing the data collected from past missions, scientists can create detailed maps that illustrate these variations in regolith thickness. Scientists have discovered that areas with more frequent meteor impacts tend to have thinner regolith due to the constant disturbance and erosion. By studying these patterns, researchers can better understand how the lunar surface evolves over time. The analysis of past missions has also revealed that certain types of bedrock lead to thicker regolith accumulations, providing insight into the Moon's geological history. The continuous bombardment of meteorites wears away the lunar surface, resulting in thinner regolith layers. This process occurs because each impact redistributes and removes material from the area. Over time, these impacts create a pattern of erosion that can be observed across the Moon's surface. These impacts also expose fresh bedrock, which can then be studied for further clues about the Moon's past. The persistent nature of these events allows scientists to track changes over long periods of time. Observing these changes helps in understanding the dynamic processes shaping the lunar surface. This data is crucial for planning future missions and safe landings on the Moon. On July 15, 2024, the discovery of the first lunar lava tube was published in Nature Astronomy. This peer-reviewed journal is known for its rigorous standards and reliable findings in astronomy. The date of publication indicates the exact moment when this significant piece of information became available to the scientific community. Lunar lava tubes form as a result of volcanic activity on the Moon's surface, where lava flows solidify to create tunnels. These tubes are of great interest because they can offer shelter and resources for potential lunar habitation. The process of discovery involves analyzing data from lunar missions, which provides detailed insights into the Moon's geological history. This particular discovery was made possible by advancements in remote sensing technology that allowed scientists to study the Moon's surface with unprecedented precision. By understanding these lava tubes, we gain a deeper comprehension of the Moon's internal processes and its evolution over time. These subterranean passages could provide stable temperatures and protection from radiation, crucial for human survival on the Moon. They are typically formed when lava flows along the surface, cool and harden, leaving behind hollow spaces beneath. By studying these formations, scientists aim to uncover more about the Moon's thermal history and the mechanisms that shaped its surface. The presence of these tubes hints at a complex past of lunar volcanic activity. Careful examination reveals that lava once flowed freely beneath the Moon's surface, creating intricate networks now solidified. Remote sensing data has enabled scientists to map out these hidden structures with remarkable clarity, revealing their extent and potential usability for future missions. The LUGO mission is a scientific endeavor focused on studying the Moon's thermal history through irregular mare patches and lunar lava tubes. These irregular mare patches are peculiar geological formations on the lunar surface, offering unique insights into how the Moon has cooled over time. Scientists have long been intrigued by these patches, as they provide a window into the Moon's past thermal activity. The mission involves carefully analyzing these regions to understand the Moon's internal heat and its evolution over billions of years. By examining lunar lava tubes, researchers hope to uncover more about the volcanic processes that shaped the Moon long ago. This detailed study will provide a clearer picture of how our celestial neighbour has changed and evolved since its formation. The heat within these patches tells us about the Moon's initial cooling rate. Observations from lunar orbiters have revealed temperature differences across these regions. These variations suggest varying depths and compositions of lava flows, giving insights into past volcanic activity. These temperature variations indicate different stages in the Moon's cooling process, with warmer regions signifying more recent activity. The detailed mapping by lunar orbiters has provided crucial data for this analysis. This information is key to understanding the Moon's geological evolution and its heat distribution over time. These temperature variations also help scientists determine the age and origin of the lunar lava flows. The heat detected by orbiters indicates areas where the Moon's interior was recently active, allowing for deeper insight into its geological history. Understanding these thermal patterns is crucial for mapping out the Moon's internal structure. Observing the differences in temperature across irregular mare patches enables researchers to piece together the sequence of events that shaped the lunar surface over time. The Gateway in lunar orbit is part of the Artemis infrastructure. This structure orbits around the Moon, serving as a key component of NASA's new lunar exploration program called Artemis. In ancient Greek culture, Artemis was revered as the goddess of the hunt and wilderness, her worship practices being integral to their religion. The Gateway will facilitate upcoming missions, known collectively as the Artemis generation. These missions aim to inspire a new wave of explorers, much like how the ancient Greeks were guided by their beliefs in Artemis. This lunar outpost is designed to support various spacecraft and astronauts, providing a strategic base for future exploration activities around the Moon. The location of the Gateway allows it to act as a critical staging area for missions that require precise maneuvers and positioning near the lunar surface. Its role in enabling prolonged stays in space marks an advancement in humanity's quest to understand our celestial neighbour better, contributing to scientific research and technological innovation. The Gateway's position in lunar orbit allows for continuous monitoring and detailed observation of the Moon. It serves as a crucial link between Earth and the lunar surface, enabling efficient data transfer and communication. The knowledge gained from this outpost will provide insights into the moon's composition and history. This advancement is a result of technological progress that has made long-term space habitation feasible. The Gateway's presence near the moon offers a stable platform for experiments that would otherwise be affected by Earth's gravity. Its strategic placement enables unobstructed views of the lunar surface, crucial for understanding its geological evolution. The outpost is equipped with advanced sensors and cameras to record these observations continuously. This continuous data collection will help scientists study the moon's rotation and other dynamic processes in greater detail. The name Artemis echoes from ancient Greece to the modern world. This name was given to the moon by the Greeks, honoring their goddess of the hunt and wilderness. It has been passed down through generations, maintaining its relevance in cultures across time. The name Artemis is a reminder of our connection to the past, even as we explore the future. People around the world recognize this name, tying it to the celestial body that lights up the night sky. In using this name, we preserve a piece of history that has traveled with us through centuries. The name Artemis has been consistently used, appearing in literature and poetry across languages. It is a symbol that unites us all under the same sky. This connection to the past brings comfort, reminding us of our shared humanity. Learning about this history helps us appreciate the continuity of human experience. Artemis's name endures, a steady beacon in our collective consciousness. It bridges epochs, weaving together eras with its familiarity. This link is evident in global usage, from ancient myth to present day. Understanding this name's journey reinforces our sense of collective identity. The name Artemis persists in common parlance, echoing through generations like a softly spoken secret. It is woven into the fabric of human culture, an enduring thread that binds us together. Through stories and legends, we have inherited this moniker, carrying it forward with reverence. Its longevity underscores our collective memory, reminding us of the stories passed down by those who came before us. The moon's diameter is approximately 3,474 kilometers, 2,059 miles. This measurement was refined over time through careful observations and technological advancements. The moon appears to us as a constant presence in the night sky, its silvery glow illuminating our world. Its actual size has been determined by astronomers using sophisticated instruments that measure its visible diameter with precision. The moon's surface, a landscape of craters and seas, reflects sunlight back to Earth. This reflection allows scientists to accurately calculate its dimensions. Through telescopes and spacecraft, we have gained detailed insight into the moon's true size. Its substantial diameter is a result of billions of years of formation and evolution within our solar system. The moon's diameter allows it to exert a significant influence on Earth's tides. This size also enables the moon to appear roughly the same angular size as the sun, making solar eclipses possible. Its large diameter is indicative of its substantial mass and gravitational pull. Precise measurements of this diameter have been made using laser reflectors left on the lunar surface by astronauts. Each full moon presents a disk that spans about half a degree in the night sky, providing a consistent visual reference. Advanced lunar probes have mapped the satellite's topography in fine detail, confirming its vastness. The large diameter of the moon is crucial for maintaining Earth's axial tilt and stabilizing our planet's climate over long timescales. The moon's diameter is also essential for studying its internal structure through seismic activity. As light waves reflect off the lunar surface, they reveal its rugged and varied terrain. The consistent size of the full moon throughout history has been vital for ancient timekeeping and calendar systems. Observing changes in the moon's apparent size during lunar phases provides insight into its orbital mechanics. The diameter of the moon's inner core, a dense and solid mass rich in iron, is approximately 480 kilometers. This central region is the innermost part of the moon, buried deep beneath its surface. The size of this core was deduced through studies of the moon's gravitational field. Seismic waves traveling through the lunar interior also provided valuable insights into the moon's internal structure. These waves revealed a solid core, different from Earth's liquid outer core. The density of the inner core suggests it is primarily composed of iron. This dense and compact heart lies at the very center of the Moon, far removed from its dusty surface and harsh radiation environment. The solidity of the Moon's core is crucial for understanding its ability to maintain a stable magnetic field, albeit weak. Its formation can be traced back to the early days of the solar system, when heat from impacts helped shape this inner region. The detection of seismic waves within the lunar interior provided evidence supporting the presence of this solid core. Additional data from spacecraft missions further bolstered our understanding of the Moon's internal structure. The solid core of the Moon plays a vital role in its overall stability, as it affects the distribution of mass within the satellite. The lack of fluid movement within this region implies that the Moon did not experience significant differentiation processes later in its history. Observations from lunar landers and orbiters have allowed scientists to map out the detailed structure of the Moon's interior, confirming the solid nature of its core. The Moon's density reveals a core that accounts for about 1.7% of its total mass, similar to the Earth's core. This density is not something we can see directly, but rather infer through careful measurements and calculations. Scientists have used seismic data to map the interior of the Moon, just as they do with the Earth. These seismic waves travel differently through various materials within the Moon, allowing us to deduce its internal structure. The core is believed to be dense due to the presence of heavier elements like iron. Despite being so far away from us, the Moon's composition offers insights into how our solar system was formed. Over time, these findings have helped refine our understanding of celestial bodies and their origins. The Moon's density indicates it formed from the same material that created Earth, suggesting they share a common origin. Seismic data from lunar landings helped scientists interpret these findings accurately. The slower speed of seismic waves through denser core areas confirmed its composition. By studying our closest celestial neighbor, we gain deeper insights into planetary formation processes. The core's density suggests that early in its formation, heavier elements settled there due to gravitational forces. These internal findings align with the Moon's overall composition being similar to Earth's. The consistency of data from various lunar missions supports this interpretation of the Moon's interior structure. Seismic waves from lunar impacts and landings revealed variations in the Moon's interior. These waves travel more slowly through denser materials, helping scientists map out the core. This mapping process is similar to how geologists study Earth's interior. The consistency of these findings across different lunar missions lends confidence to our understanding of the Moon's composition. Magnetic field measurements on the Moon reveal that it does not have a global magnetic field like Earth, but has localized magnetic fields in some areas. This means there are specific spots on the lunar surface where the Moon's magnetic properties differ from the rest of its crust. These anomalies are likely remnants from earlier times, when the Moon may have had a stronger and more uniform magnetic field. The elliptical orbit of the Moon around Earth, with a semi-major axis of about 384,400 kilometers, adds another dimension to these magnetic peculiarities. As the Moon travels this path, its rotation period relative to Earth of 27.3 days ensures that different areas of its surface face Earth at various points during its journey. Over time, scientists have used these orbital dynamics to map out the lunar magnetic fields more accurately, helping us understand the complex history hidden beneath the Moon's dusty surface. This data suggests that the Moon's core may have cooled and solidified over time, leading to the decay of its magnetic field. By analyzing these localized fields, scientists aim to piece together the Moon's past magnetic activity. The presence of magnetic anomalies also indicates possible variations in the lunar crust's composition and thickness. Ongoing research continues to refine our understanding of these unique lunar characteristics. The Moon's magnetic anomalies offer insights into its early geological history, revealing a time when it might have been more magnetically active. These remnant fields are believed to be fossilized in the lunar crust due to ancient magnetic activity. They were first detected using magnetometers carried on lunar orbiters and later mapped with greater detail. The study of these anomalies provides a window into the moon's formation and evolution, offering clues about its past environment and dynamics. The rotation of the molten outer core generates a magnetic field, although it is not as strong or global as Earth's magnetic field. This magnetic field forms as electrically conductive material moves through the lunar core, creating an electromagnetic effect similar to how a dynamo works on Earth. The moon's smaller size and slower rotation contribute to its weaker magnetic field compared to our planet. While not visible from space like Earth's, traces of this magnetic field have been detected on the moon's surface by robotic missions. These remnants provide evidence of an ancient lunar dynamo that operated billions of years ago when the moon was still geologically active. The magnetic field, once strong enough to deflect solar winds, has since diminished over time as the moon's interior cooled and solidified. Scientists have studied lunar rocks and soil samples brought back to Earth, revealing traces of magnetism that hint at a past magnetic field. Satellites orbiting the moon have measured fluctuations in its gravitational pull, offering clues about the liquid core's behavior. The moon's crust, now cooled and solidified, retains signs of this ancient magnetic field in certain mineral formations. These findings suggest that the lunar dynamo ceased operating when the moon's interior lost enough heat to drive the movement of electrically conductive material. The discovery of this ancient lunar magnetic field has provided valuable insights into the moon's past. By analyzing these remnant magnetic traces, scientists can better understand how the moon formed and evolved over time. The detection of this magnetic field in lunar rocks indicates that the moon was once a more dynamic place than it is today. As the moon continues to cool, further studies may uncover additional details about its early magnetic properties. One prominent theory suggests that the moon formed from the debris left over after a giant impact between Earth and another Mars-sized body called Theia. This event, occurring billions of years ago, left our planet with a significant companion. The moon's presence creates tidal effects on Earth, causing the oceans to ebb and flow in rhythmic patterns. These tides are a direct result of the gravitational pull exerted by the moon on the waters of our planet. As Earth, the Sun, and the moon align and shift positions, they generate different phases of the moon. The changing light reflecting from the lunar surface creates these cycles, influencing the illumination we see from night to night. This cycle has been observed and studied for centuries, providing us with an understanding of the moon's influence on our world. These changes in lunar light also affect wildlife patterns, as many animals rely on these rhythms for their behavior. Observing the moon's phases has helped astronomers track its orbit and calculate its influence on Earth's tides with precision. By studying the moon's surface, scientists have gained insights into its composition and how it differs from Earth's crust. Understanding these differences sheds light on the processes involved in the formation of both bodies. The moon's light also influences plant growth, as some species use it as a cue for germination. The reflection of sunlight off the moon's surface provides enough illumination to affect nocturnal creatures' behavior and migration patterns. Observing these changes over time has allowed scientists to predict lunar phases with accuracy. The study of moon rocks brought back by astronauts has further deepened our understanding of the moon's composition and history. Mare Imbrium, a vast sea on the moon's near side, came into existence from a massive impact event that took place roughly 3.85 billion years ago. This area is smooth and flat due to lava flows filling the crater left behind by this colossal collision. The impact was so immense that it not only shaped the surface, but also scattered debris across the lunar landscape, leaving remnants of the ancient event for us to study today. By analysing the material and observing the crater's structure, scientists have determined the age and scale of this cosmic occurrence, giving us insight into the early history of our celestial neighbour. The flatness of Mare Imbrium hints at a layer of basalt lava solidifying over time, creating the smooth surface we see today. This ancient impact event also sent shockwaves through the moon's interior, causing seismic activity that further shaped its terrain. By examining the surrounding craters and their ages, scientists deduced the timing and magnitude of this cataclysmic collision. The distribution of debris from the impact helps researchers trace the trajectory and origin of the impactor. The smooth surface of Mare Imbrium is a result of millions of years of lava flow, gradually filling in the crater created by the impact. This solidified lava layer also helped to preserve the impact site, allowing scientists to study it today. The extent and distribution of the basalt material point to repeated volcanic activity over an extended period. Careful examination of these materials under various lights and spectra has provided insights into their origin and evolution. On July 20th, 1969, the first humans landed on the Moon during the Apollo 11 mission. This historic event was part of a series of space explorations that totaled 17 missions, with only 6 successfully achieving manned lunar landings. The journey to the Moon involved navigating through vast distances and understanding the unique characteristics of lunar surfaces. The analysis of rocks brought back from these missions revealed insights into the Moon's formation, suggesting a process involving magma ocean crystallization that shaped its crust over time. Each successful landing marked a significant step forward in humanity's understanding of our celestial neighbor, paving the way for further exploration and discovery. Each mission provided valuable data about lunar terrain and composition, refining our knowledge of its geological history. This understanding was crucial for planning future missions and ensuring astronaut safety. Samples collected from the surface were subjected to rigorous analysis in laboratories on Earth, revealing the Moon's complex structure and evolution. These findings have since influenced scientific theories about the early solar system. The Moon's rocks, brought back by these missions, offered clues about its past. By studying them, scientists gained insights into the early stages of lunar formation. These samples also hinted at the conditions present during the Moon's birth. Each mission provided new pieces to the puzzle, helping researchers assemble a clearer picture of the Moon's history. Each lunar sample was carefully catalogued, its origin and composition meticulously recorded. By observing these samples under a microscope, scientists could see the individual crystals that formed during cooling periods. The variation in mineral content between different rocks provided clues about the Moon's internal temperature history. These observations were further validated by laboratory experiments that simulated lunar conditions. The last time humans set foot on the Moon was during Apollo 17 in December of 1972. This mission marked a significant moment, being not only the final manned trip to our lunar neighbor, but also holding the record for the longest stay on its surface at 12 days. During these extended visits, astronauts had more time to explore and gather samples, such as the olivine basalt collected by Apollo 15. These rock samples reveal a complex geological history of the Moon, highlighting the diverse processes that shaped it over time. The lunar surface, bathed in sunlight, retains its secrets until they are carefully extracted and studied back on Earth. This final mission underscores both the achievements and the pauses in humanity's exploration of space. The extended lunar stays allowed for deeper analysis of the soil and rocks, uncovering evidence of ancient volcanic activity and meteorite impacts. By examining these samples under Earth's advanced microscopes, scientists have gained insights into the Moon's internal structure and early formation. The prolonged exposure to the lunar environment also enabled the testing of various equipment and techniques for future space exploration. The data collected from these experiments continues to inform our understanding of the solar system and beyond. These extended stays on the lunar surface have provided invaluable data, deepening our comprehension of its evolution. The soil and rocks collected contain essential clues about past events that shaped the Moon's landscape. Each sample meticulously examined under Earth's microscopes reveals intricate details of the Moon's geological history. The equipment tested during these stays has paved the way for future space missions, ensuring they are well prepared to face lunar conditions. And that is where we will leave the Moon for tonight. The facts will still be true tomorrow, and this video will still be here whenever you need it. Sleep well.